So next up, we have Mini TT, security technologist at Dell, who will present her talk titled End-to-End Device Security Enhanced by Hardware. Mini has worked in research and development with Philips and ABB, producing innovative products, publications, and patents. She has experience in defense, semiconductors, consumer electronics, substation automation, and industrial measurements. She had started her career with Bharat Electronics, developing command and control systems for Indian defense. Her specialization is in cybersecurity, embedded systems, and system architecture. She holds an MTech in embedded systems from BITS Pilani and a degree in computer science and engineering from the University of Kerala. It's with great pleasure that I invite Mini TT to deliver the talk. Over to you.
Okay, thank you. Thank you so much, Anushka, for that nice introduction. It's a very interesting topic that we have today. Like what we are trying to cover is there are various activities that happen in the life cycle of a device, and then how can we use the underlying hardware to enhance the security. That is what we are trying to cover in this session today. That's what we say, end-to-end security enhanced by hardware. I'm Mini TT. I work with Dell Technologies in the space of embedded system security for server management. So let's start. So what are we talking about when we talk about network devices? There are a large spectrum of devices. Like what can happen is all these things which we are talking about, they are all those Internet of Things kind of devices that we are talking. Or if you look at the entire architecture, there could be edge gateways that are doing the compute. And then over the internet boundary, then we have these cloud systems which we are connecting to. And when we consider any of them, all of them have an underlying hardware, and the security that is required is enhanced by the underlying hardware. So how much of our security we are trying to do, just by looking at the software layers above, we will not be able to achieve the required security unless the foundation on which we are working on below is secure. So that is what our talk of today. So these are some of the examples which I'm trying to put there, like what it means to be when a device is. It could be this Internet of Things devices. It could be the edge gateway devices. It could also be the underlying infrastructure that we are talking in a data center kind of an environment. So let's see what all happens in the life cycle of a device. So during the life cycle, first primarily it is manufactured, that is in the domain of the manufacturer. Say like companies like Dell Technologies where I'm working on, that is where the manufacturing happens. And then it goes through various phases before we decommission. So that is, there are multiple stages in the supply chain. That is one, it goes through various hands. Then ultimately in the operational environment where is it supposed to be working, a provisioning will happen, and then it will be continuing to work there in the provisioned environment. That is its major primary purpose of work is in the environment where it is provisioned, it is an operational stage. And later on, we have a lot of management functions that will happen. That would be like, say, firmware updates. There could be some security vulnerabilities that would have come to notice of that. So maybe you will do the patch management for that. All those are the management activities that would happen. Or due to some kind of upgrade, there could be configuration changes. And then ultimately we do a decommission. At the time of decommission, we also need to make sure that all the data is protected or they are destroyed safely. The secrets are discarded and the data is destroyed. And if there is any need for maintaining it for further time after that, then we may need to keep safe environment to keep it secure for any kind of requirements to keep it for long duration purpose. So all these are the needs of the device lifecycle activities that we are talking. So let us look at what are the domains we are talking. So now I told that, okay, we have a manufacturer where the domain of the manufacturer is different. So when we talk about trusted identities, it could be certificates, it could be any other kind of a trusted identity of the device. The domain in which the operation happens, you may have a trust anchor to validate, to see whether it is coming from the manufacturer's domain, say for Dell Technologies domain, that is one. Then in the supply chain, there could be integrators who create a larger assembly of devices. make a system out of taking all of these individual items, that is where this next activities will happen. That could be the supply chain, or it goes through various hands as part of the transfer of that. All of that is coming into the supply chain. And then it is the operational environment. And further, it could be service. That is something which we may not see all the time. But then service is during the life cycle, somebody needs to service, and there might be some need for a replacing parts which has gone bad. So those are the kind of service activities that will come. So in each of them, these are different trust domains, and how do we establish trust where all these handover activities happen? So that is one different kind of trust domain that we are talking. So when we move from a manufacturer to supply chain and then to an operation, ultimately to do its primary purpose, it has to get identities in the domain of operation. Identities, I mean, say, for example, for a TLS kind of communication, you need a TLS certificate with the associated key pair. So how do we generate that key pair and then move from one domain to another? And these are some of the activities that happen during the life cycle of the device. It's more detailed than what we were seeing before. That is, you do the manufacturing, then you do the installing, commissioning. There will be various steps which we call as a bootstrapping. Bootstrapping is when the first time it is getting into an operational environment. And then in the operational environment, the application is running, and later on it could be software update. The application may be reconfigured. And again, you must be coming into the application running stage. That's again the operational activity. Then you may need to have maintenance. Like it could be that it's cleaned up and then you are using it in a different environment. And there may be needs for a rebootstrapping that could happen. And there could be parts replacement, or maybe the entire assembly is replaced. You take it out and then you put something else because it has gone bad. And there may be re-ownership, or maybe you are recommissioning into another environment when a re-ownership happens, or it could also be totally decommissioning that happens. So all this what we are talking about. And so this interoperability is a activity that we are talking in each of these kind of environment. And let us talk about in all these places, what are the security threats that can happen. This is a large list of security threats that could happen. I'm just putting some kind of examples so that you understand what all could happen when we are talking of physical entities, physical devices, what are the kind of threats that are there possible. This is not any exhaustive list in any manner, but they are more to give a guidance on what it could be, what can be the case of threats that we are talking. So first we are talking there could be vulnerable software. So there could be buffer overflows that can happen, which somebody could exploit. And then maybe a lack of authentication that can happen. If it is buffer overflow, that gives a space for a lot of things that can happen. It can cause authentication bypass, and then, or it can also cause somebody else to run a remote shell, and all those are possible vulnerabilities that can happen. And then it could be privacy threat. That is privacy threat. It could be tracking your location and usage, what you are doing, or it could be traffic interception, and then somebody is getting hold of the data that we are talking. Or they could also be cloning. Cloning is like during your manufacturing process, if it is an untrusted environment, they could easily clone the physical characteristics. The look and feel and all could be the same. The firmware UI may appear the same, but then it could be a degraded functionality that is running, not what the trust that is coming from a genuine manufacturer. It could also be backdoor. There could be backdoor introduced into the device if it is going via untrusted environments. And the deployed things must be compromised in any manner. So you might be thinking that you are running a good device and which is having good trusted firmware, but ultimately it could be running a cloned device with degraded functionality. It could have other security flaws. Means the device in itself will become your problem area in the deployed environment and your system. So this is something that could happen as a cloning. And then for further threats, it could be a malicious substitution. Malicious substitution, what could happen is during installation of a thing, their good quality device might be replaced by a similar variant of lower quality. And the motivation could be cost savings, or it could be that the installation of lower quality things it may reduce in the operational cost. So somebody might be saving some money by doing that. They can subsequently resell these genuine devices to gain further financial benefits. Or other motivation could be to inflict damage to the reputation of the organization. That could be another reason for malicious substitution. So what we have actually talking about, say a Dell product, a look and feel of a similar product, but something else. That's what we are talking about substitution. And eavesdropping, which many of you might be already knowing, that is during the commissioning of a thing into a network, it could be susceptible to eavesdropping. The eavesdropping could be on the keying material itself, or on the security parameter or configuration settings are exchanged and clear during a medium. That is, if it is specifically a wireless medium, that could be a possibility. The cryptographic algorithms used are not suitable for the lifetime of the device. You could get the keying material, and then later on, they could use that keying material to establish communicating with rogue entities during this time. So all those are possible with eavesdropping as an attack. So they could get hold of the keys itself, security parameters, configuration, which can be used for launching or mounting further attacks. And another one is about a person in the middle kind of an attack. Like we are talking about in this situation, instead of the communicating entities, you are actually talking to some other rogue entities. So in that person in the middle, the previous steps could be used for starting this kind of a person in the middle attack. And let us look at some more security threats that we are talking. So it could be firmware attacks. The firmware attack is you are maliciously replacing the firmware with another rogue firmware. So the physical device could be the same, but if you don't have good secure boot, these are all things that can happen. If you don't have a secure boot and signed signature validation at each step of loading your firmware and applications, somebody could load another malicious firmware, and then it could be running the malicious firmware instead of the genuine firmware that is supposed to be running on that. And it could, another case could be extraction of private information. So many of these things, there can be certain environments where, especially in the IoT kind of environments, I'm not talking about a data center environment, but in an IoT environment, such as sensors, actuators, they are most of the time could be physically unprotected in their ambient native environment. And then they could easily get hold of the physical device, and using that physical device, somebody can say disassemble or then even put probes into it, and then they can also extract private information physically from those devices. And it may not be used for an attack on that same instance of that device. Instead, they could use it for launching attack on another instances of the same families of devices. These are another kind of security threat that could exist as an extraction of private information. And then there is denial of service. If you have only limited memory and then limited compute resource, you could do resource exhaustion, or you could interrupt the network so that you are not able to reach to the network and you have an availability problem. All those are things that could happen when we are talking of security threats. These are some of the examples of the security threats that can happen in an environment of physical devices, whether the physical device is say small and IoT kind of very small and compute device, or it could be large computing devices. In all these cases, if the underlying hardware is not supporting, and if you do not have sufficient security controls in place, all of these kind of things could happen as attack scenarios and security threats. So let us move forward and look at certain scenarios. These are scenarios in which we use this hardware supported security, which will come into picture. So I'm not putting once again an exhaustive kind of scenarios, but certain sample scenarios where this could come into picture. So let's talk about identities. Identities are, we need a cryptographic identity of physical hardware device, like which is bound to that hardware itself, not something that is as a serial number, say, they don't have a cryptographic protection. But if we are talking of device identities, say, for example, 802.1 AR talks about initial device identifier, which is in the domain of the manufacturer, or they also talk about a locally significant device identifier, LWID, which is in the domain of the operation. So they are the domain of significance, which we were talking in our introductory time. So these are all device IDs that we are talking. So when we are talking of IDEV ID, initial device identifier, they are manufacturer provided. They are never expiring. It's like associated to that one instance of the hardware, like more like a fingerprint of the hardware that we are talking. They are never expiring, and they are usually not coming into a publicly trusted place. Like, say, for example, if you are talking of a web server certificate, which is on a hosted web service, they are usually in the public trusted trust anchors, like many of the CA providers. And you will have those trust anchors in your Windows store or Linux store or some, or those kind of places it will be available. But in these physical identity certificates, usually you may not be in a publicly trusted environment. And later on, we move from an initial device identifier to a locally significant identifier that is in the operational domain or the customer's domain. So these are usually used as a communication identity. They are also renewed periodically because they are regularly used. So you can once again generate a certificate signing request and then get it signed when it is about to expire, do all that. So those renewal happens. And in many situations, these are publicly trusted. Not always, but in many situations, these are publicly trusted in the domain of the operations. Any questions now, or shall we continue? Nothing. Okay, let's continue. And let us come to some other scenarios that we are talking. Another scenario is about attestation. So attestation is a concept which about how do you know that the device is in a good state? Are you whom you claim to be? And can you provide an evidence that a third entity can say that, okay, I can attest to that you are running a good firmware and you are also having the physical identity that we are talking about. So this is the concept of attestation. So there are like multiple entities that come into picture, but then fundamentally there will be three entities that we are talking. The attester, that is the device in itself which is getting attested. So they are the ones to provide evidence that, okay, see, I'm in a good state. I'm running good firmware. You can attest to various entities, but right now we are speaking about attesting to your physical identity, that is hardware identity, attesting to the firmware identity. We could also attest to many other entities in doing this process. And then there is a verifier. The verifier is the one tells that, okay, whatever information that you have provided, is it something that goes against what is prior knowledge? Prior knowledge verifier, do I trust, do I have a trust anchor that is there? Or if you are giving me a firmware, a signed firmware hash, a firmware digest if you are giving, do I trust that? Is that matching to the hash values which I'm expecting? All those are something which a verifier can provide. The verifier will be using in turn further database of reference values to do all these kind of items. So I have not showed all the actors in the picture, but there will be further actors who are providing information for reference measurements, reference values, and trust anchors, and all those kind of information. And ultimately, it will come to a relaying party. The relaying party is the one who is depending on the work done by this entity device, that is the attesting entity. So the relaying party ultimately will decide to work with this device or not work with this device based on the attestation information that we are trying to collect. So here I am showing two models of attestation. So one is where we call it as a passport model. A passport model is like the attester gives evidence to a verifier, and the verifier gives the attestation result, and then the relaying party uses that information. That is a passport kind of a model. There could be another model that is a background check model, where the relaying party first collect evidence from the attester, and then they can provide that, the relaying party can provide that information to a verifier, and the verifier gives an attestation result, and the relaying party decides whether to continue all that. So these are all, there are various standards that are coming around in this attestation, like IETF has a RATS working group, other industry consortiums like TCG, DMTF, they are all working on various other solutions for doing this attestation. So this is a concept of what do you mean by attestation and how do you do this attestation. This is one case where we are talking. Let us look at some more scenarios. Say, let us look at provisioning as a scenario. Provisioning is a process where you are obtaining an LDAV ID. That means the device is coming from a factory with a birth certificate, and you trust the birth certificate, then how do you know that, how do I get entities which like cryptographic identities which I can use for talking in the operational environment? That is what we call it as a enrollment into the operational domain or provisioning into the operational domain. So what could happen is that you can run a discovery protocol, like we are talking about a zero-touch provisioning. Zero-touch means the situation is like somebody takes physically a device and connects to the network. That's the only action that they perform. And then it has to automatically obtain identities in the operational target environment, and it has to start operating. Like in certain environment, these are all could be mandatory, because it may not be all the cybersecurity experts or security experts who are doing this kind of action of taking a device and connecting it to the network. It could also be like people who are working with a screwdriver. All what they may know is to disconnect physically and then to put a new device and then connect it physically and then tighten the screws. That may be the only one thing which they are aware of. And you may not be able to talk about the cryptographic identities and digital certificates there. So in this kind of situation is where we need this zero-touch provisioning. So the process is somehow we run a discovery protocol. That could be, for example, it could be an MDNS, a multicast DNS, and then the device can prove its identity to the network which it is trying to connect, because it is coming with a birth certificate. And the network can prove its identity to the device. So the device can decide, do I begin to trust this network or not? And the network can decide, do I begin to trust this device? So if the trust establishment happens, then the device can request for an LWID and the network can grant an LWID, and now it has an identity in the operational domain in which it can operate. So this is a provisioning scenario which we are talking, and there are multiples of once again industry references that are available. Like from IETF, there is Brisky that is coming in, and there is something which is called as Intel Secure Device Onboarding. That is another solution. And ARM, there is a solution for Pelion. All those are solutions which can be used for provisioning into an operational domain. So if you look at Microsoft Azure, they have Azure Device Provisioning Service. That's all used for this kind of operations. So let us come to the story. The story is imprinting. Imprinting is a term that is used for like when an entity first begin to trust a network. That is the reference that we are talking of as imprinting. In a secure zero-touch provisioning, imprinting is a concept. Like if you know this Mowgli story, the Mowgli forever believed that this animal kingdom is its family, because the Mowgli got imprinted onto that animal kingdom. So it never knew what that is or something else. It doesn't know about anything else. That is what we call as a trust on first use kind of a scenario. And that is where the device begins to trust the first network where it gets connected to. So this is not like you are proving to identity each other. Instead, this is a concept where we call it as a trust on first use. Like you are seeing that duckling, this is also one another, like the understanding is that a duckling, when it is coming out of its egg and when it is first hatched, it doesn't know which is its mother. So when it looks around, the first moving object that it sees, which makes a sound, regardless of what it looks like, the duckling will begin to believe that the first moving object is its mother. So that is what we call as an imprinting. So these are some examples that we call as a trust on first use. And this imprinting as a concept is used for getting connected to the network. So that means in our previous scenario in which we talked about the device, when someone physically had the possession of that device and when they took it and connected to the network, the first network to which the device is getting connected to, it could begin to believe that this is a genuine network which I am joining in. So that is where we talk about imprinting as a scenario. This has its own security gaps. That is why we are talking previously about doing mutual trust establishment. The device can ask the network, are you the network which I should get connected to? In those kind of scenario, we are talking of doing an explicit trust establishment. The device prove its identity to the network and the network prove its identity to the device. Both will happen. That is not a trust on first use scenario, but in trust on first use, you just trust a network to which it is connected to. Like our Mowgli story, Mowgli never even knew that it was not human beings that they don't belong there, but the first object which it got connected to, that became its environment. Similarly, the duckling, if it gets first moving object, it goes with that. That is the concept of trust on first use. It has its own flows because even though it's for a short time, there is still a time where somebody can intercept the network and do malicious activity. So explicit trust is what is expected. And standards like Brisky, bootstrapping remote secure key infrastructure coming from IETF, they are all talking about explicit trust establishment for getting into a network. Now let's look at some more scenarios. Say in this situations, till now we were talking about device as a single entity. The device need not necessarily be a single entity. It could also be composite devices, which has multiple field replaceable units. Like the device in itself is composed of other devices. You can think of as a robotic assembly, which has a lot of moving parts, which are replaceable parts. Or if you are talking of in the industrial world, there could be like composite devices, which has multiple pieces. Or in the server environment, you may have replaceable items for your network controllers, network cards, storage cards. So the security of the assembly is what tells what is the security of the system. Now, and the assembly security is established based on the assembly security is established based on the security of the individual units and the assembly itself, not based on one entity and one identity. That is where we talk about composite devices, where multiple identities come into picture, which together form a composite identities. And they could be heterogeneous or homogeneous. Sometimes it can be a flat kind of a thing. They don't have a hierarchical structure. And they could be treated as a machine, or they could be treated as a platform. And the identity of the parts and the identity of the composite all are to be considered. And there could be hot swap scenarios where you change one part and you insert another part. And there could be also firmware update. The firmware update of the assembly, that could be one if you're talking of a hierarchical system, or it could be a firmware update of the individual pieces that we are talking. So till now, we talked about various scenarios where we need all this kind of support. Now let us look at how hardware can support to achieve all these goals and the scenarios that we are talking. So the first one is a secure boot. If you do not have a secure boot, you have no idea whether the firmware that is running in the device is a trusted firmware or not. You can load any untrusted firmware and then also could be doing your work. So the hardware root of trust, that is where you start your secure boot, and you have an immutable startup code, and you have an immutable keys which are used for authenticating your first mutable code and then starting with the boot process. So usually the chip vendors provide facilities like an eFuse array, so that you can, the firmware vendors or the application vendors can permanently fuse the public key or its corresponding hash value into the hardware. And from there, you can establish the further trust, like your U-boot, the operating system application, all that can establish trust further. So this is where one scenario where you will require support from the hardware to achieve your security needs. Let's look at some more scenarios where the hardware can support for realizing this. Say you have the cryptographic identity of the hardware that we were talking about, which is bound to the hardware instance, the specific instance of the hardware. So that means the specific instance of hardware needs identities which are bound to that hardware itself, where you could use solutions like, say, puff, like is your physically unclonable function, or it could have randomness where we are able to derive keys within the device itself. And maybe there are keys which are not exportable. You can never take it outside, so that it is bound to that hardware. You can have random numbers, then key generation functions, and you can bind the serial number of the physical device to a certificate from a infrastructure that is providing certificates. All those could happen. And these are another environment where in which hardware support will be necessary for establishing device identities. Because all what we talked previously, device identity and all are starting points which we use for establishing operational security and provisioning. So device identity becomes an important part, and then how hardware can support to provide all these kind of device identities keys. And then we have other scenarios where we are talking of secure storage, like we need to store secrets or other private information securely. So there are solutions like, say, Trusted Platform Module, TPM, which provides facilities for generating keys, and then we are never able to take it out from the chip itself. So all what is available is you have operations. You can perform operations using the keys, but you can never get the key itself outside. So you don't have access to the private key, but you do operations like signing, decryption, all that using these. That is where solutions like TPM and all will come, where secure storage is the purpose that we are trying to do. And there are also many other solutions that are around what is required for achieving this secure storage. Some of them could be key encryption key itself. You have the device key encryption key, which will use for encrypting other symmetric keys, which will be used for doing the bulk data encryption. So these are another ways of using it. So there are multiple ways of using it. I'm just giving you a few examples of using. One is the asymmetric key itself, which is used for decryption and signing, and other symmetric keys, which could be either stored inside secure manner, or it could be that other asymmetric keys are used for securing the symmetric keys, which you use for bulk data encryption. We have some more situations that we are talking. That is about firmware identities. Firmware identity, when we say, we are talking of which is a firmware that you are running, and how do you talk about the identity of the firmware. Primarily, we are referring to firmware measurements, that is hash values, the hash of the firmware. TPM provides a very beautiful way of doing this, which they call as a platform configuration registers. So you are collecting a digest, the digest of the first stage bootloader, accumulated with the digest of the second stage bootloader and further operating system kernel applications, all that. So by doing that, you get a single digest by doing from this platform configuration register. So it's linearly building up the hash so that you will get to a single identity. So you know that, okay, by looking at the hash, are you running the firmware which we are expecting it to run there in the device? And to establish the authenticity that this firmware is coming from a genuine device, we can depend on the hardware identity that we were talking before. So this is another way of establishing firmware identity. And there are multiple ways. From the TCG group itself comes with one more solution, which is the DICE model. In the DICE model, we call it Device Identity Composite Engine. What happens is, like you could look at, say this line, you see here this line. So what happens is the firmware in itself will come as a firmware security descriptor, which is used for deriving these alias keys. So by doing this, if the firmware changes, the key also will change. So with the DICE model, you could achieve these requirements of the key being bound to the firmware that is executing. So this is one way where we could achieve firmware identities by the DICE model. The DICE model, when these alias keys are derived, they are also coming from, see, here if you see, it's coming from another unique device secret. So both of them are getting into this key derivation. That means it is bound to that underlying hardware, and it is also bound to the firmware that we are running. So this is one way where keys could be used as proving the identity of the firmware. So let us look at some more support that we would require from the hardware. That is, say, trusted execution environment, because we also need to have code which we trust for operating on that. So till now, all what we were talking were mostly related to the data at rest or data in transit kind of solution. But then there is data in use. So when you are talking of data in use, the data is already in clear and we are operating on that. In this situation, we need other hardware support mechanisms, which are, say, trusted execution environments. Like there are very popular ones. Some of them are like, say, the top model, which I'm showing is about ARM Trust Zone environment. And Intel, for example, have other solutions which they call as Intel Secure Guard extensions. These are all solutions that we can use for achieving trusted execution environment. So primarily what happens is secure enclave is created, and the secure enclave has its own enclave code, and then to manage that there are entry tables, enclave code, and the stack and heap associated to that secure enclave. So when the secure enclave is using like your other app data and all, which are usually run with, which does not require that kind of protection, they don't have access to that secure enclave, and there is no easy way where you can transfer data from the secure enclave to other memory area. Like for example, you don't have DMA paths, or if you transfer from the secure enclave to outside, you will have on the bus encryption that will happen, so that you will never get hold of it in clear. So those are other supports that are possible from the hardware environment for trusted execution environment. Like beyond this, to achieve this kind of data in use privacy, there are other algorithmic support that we can use for say secure multi-party computation or confidential computing, this homomorphic encryption and all that, but they don't necessarily depend on the underlying hardware. We are talking here about how can hardware support trusted execution environment and data in use protection. So I am coming to sort of a summary on what we were talking about. So we spoke about various topics about hardware root of trust. We talked about the device lifecycle, how it goes through, and then what are the implications at each of the stages, and how key generation can be used from the underlying hardware. Composite devices, how they can be using multiple pieces, and how the assembly has the security without at the same time having the individual pieces having the security. And to prove firmware identities, sometimes it could be the underlying device that itself may be signing the firmware hash or the firmware digest. We spoke about trust on first use concept. We spoke about attestation, the device identity, composite engine, and some scenarios of firmware update in the lifecycle of the device. And we also elaborated on some of the security threats that could happen. And there was secure enclaves, secure protected enclave. How can that be used for achieving data in use protection? Those are the things that we were talking. So to summarize, what we are coming to and then telling is, like, this is the house that we are trying to construct. That is the software house that we are trying to construct. And if we are talking about the house construction, the underlying hardware that behaves as the foundation on which we can build the security. So whatever comes, whether it is rain or the streams that come, if you don't build the house on an underlying solid platform, then the software alone will not give you the security that is required. Instead, we build based on the underlying hardware, so that we get the security that if it can withstand various kind of attack scenarios that can happen. So if you are looking for constructing software and applications and systems based on a good foundation as a solid rock foundation, then start from the security, from the power on of the hardware itself, and then depending on the hardware for achieving further state of the software security. Like whatever we talk about, the HTTP security, the OWASP security guidelines, all of them are important, but then they are not sufficient unless we are talking about securing the underlying hardware and start the security from power on, from the first instruction that we start executing itself. That is the summary that we are trying to put here as a message from the talk and the session. Any questions?
Thank you so much, Minnie, for that talk. We have one question for you, actually.
Yeah.
So how will an attester ensure that a device is in a good state?
Are you talking about testing?
I'm assuming they haven't elaborated on that question.
Okay. See, some of these concepts which I spoke here, you may not be able to do a black box testing and then achieve and then verify that all that is achieved. You may need to have testing at more deeply going into the hardware at the time when your SoC or the chip is proven itself. So testing is possible, but a black box level of testing will not allow you to reach to this level. But mostly the software application testing, like your penetration testing, they can very easily cover all what we are talking about from a black box level testing. But this kind of features we won't be able to achieve most probably with the black box testing. You may have to look at more other invasive testing to look at the underlying hardware, whether the key is protected. And beyond the testing, you can also look at whether prove by design, or like it could be to that extent, it could be a formal design verification or a formal verification of whether your code is good. Testing alone is not the way to verify all this. Of course, testing has its importance. Black box testing has its importance. Other transparent, knowing how the inside of the firmware, how do you test it? That is one way. And going beyond that, there are other ways are to prove it by design, prove it by other, say, formal verification methods. Those are all ways which you can look at. Say, for example, if you look at like certifications like FIPS and all that, they have different levels of testing as well as formal verification. So all of them may have to come together to achieve and verify this kind of a hardware level security that we are speaking.
Thank you so much, Minnie. Does anyone have any other questions? We have around
1 or 2 minutes. Yeah.
A minute.
Okay, if there is no other question, then
We'll be typing it in the chat, so it might take like a minute or so.
Okay, let's wait.
If they are.
Q&A. Yes. How attester will ensure that the device is in a good state? Okay, see, the attester which I talked is the device in itself. We are talking of the verifier. So we spoke about two kinds of verification that we are talking. One is about the hardware identity, another is about the firmware identity. There can be various others. You can attest to the time. Are you holding a time? All those are ways to do. But then let's speak to hardware identity attestation and the firmware identity. So if it is a hardware identity, we are checking its birth certificate. Does that birth certificate, like when you look at the certificate chain, does it anchor to a trust anchor which is already trusted? Say a device that is coming from Dell. And if that physical device is able to provide a certificate chain, you can check whether the root certificate is the root certificate chains to a place where it is already a trust anchor which comes from Dell. So does it change to a Dell root of trust? That is one way where we can do. Other way, when we look at the firmware, you get a hash and the firmware measurement. You can have a signature on the firmware measurement, which is put by the device identity key itself. That means we know that, okay, the signature is coming from this specific device, but then do we trust that in itself? Again, you go back into the manufacturer's trust anchor and then see whether it is, can I trust this firmware? And the next one is it running the firmware which I'm expecting to run, or is it running a version? Okay, you know that it is a previous version which has known vulnerability. Is it running a previous known vulnerable version or a good version? That is where we can use reference measurement values. So you can look at reference values and does it match to the reference that you are expecting? Those are ways in which you do that good state. Yes, if you see it's a one-time programmable memory. Yes.
So thank you so much, Minnie, for this wonderful session and sharing with us your valuable suggestions. We're grateful that you spent your valuable time to deliver this talk today. So thank you so much once again for joining us in this conference.
Yeah, thank you. Thank you so much. Thanks everyone for your attention.